In this unit, we're going to investigate what's called uniform circular motion. That is motion in a circular path, and the word uniform, as it's meant before, means constant speed. So something moving in a circular path with constant speed. So to kind of illustrate some of the key concepts here, I want to consider a mass on the end of a string being twirled in a horizontal circle. So one example of that would be the hammer throw. So here we have a mass on the end of a cable, and it's being twirled around in a circle about this guy's body. Now, in the actual sport of hammer throw, this athlete would spin the mass around in several circles several times. Every time the trajectory would be changing a little bit. He'd move from one end of the ground to another end of the ground, and it'd be quite a complicated path that this mass would follow. But let's, for the purposes of today, just assume he's standing in one place and spinning this thing in a circle around himself again and again and again, always following the same circular path. So, over here, I want you to imagine that we are in a drone or a helicopter above him, looking down, just like we were in this picture here. So this circle I've drawn is the path that the object is taking. So we can say the object is maybe moving in a counterclockwise direction, or it could be clockwise, around this circle. So this circle is the path the object takes. And the first thing I want to ask is, what does the object's instantaneous velocity look like? So that means let's consider one instant, one moment in time. Let's say, for example, when the object is here. And we want to think about what does its velocity look like at that point, at that moment. Well, one way to think about its velocity at this point is to think, well, where's the next place it needs to be? And if we zoom in, we see that right after this point, the next place it needs to be is right there. So in order to get from where it currently is to that next place it needs to be, it's going to be heading sort of in this direction, right, in order to get to that next spot. And it's not going in this direction. It's not going in this direction. It's not going in this direction or in this direction. In order to get to that next dot, it needs to be going in this direction. So we can kind of see that at this point, its velocity or its movement is sort of, you might be tempted to use the word parallel. It's sort of parallel to the circle. It copies the circle right in this location there. Sort of right on top of the circle for a little bit, and then the circle bends away. Okay, so zooming out again, let's draw that here. At this moment in time, the velocity is in this direction. Now, what that means is if the cable here that the athlete is holding onto were to break, then suddenly there would be no more tension acting on this object. There'd be no forces acting on it, and it would just obey Newton's first law, which says an object in motion stays in motion unless acted on by a net force. So if the mass is over here and the rope suddenly breaks, it's just going to take whatever velocity it had at that instant, this velocity here, and it's going to keep doing that. This is something that people don't often realize. There's some misconceptions about this. A lot of people think if the string were to break at this moment, maybe the mass would shoot off in this direction. Or maybe it would kind of shoot off in this direction. Or they think it might kind of head this way and then like bend off that way. None of that would actually happen. If the string broke while the mass was right here, it would just take its velocity that it currently has and keep on moving with constant velocity in a straight line. Okay, so how would I describe that velocity? If someone had this circle in front of them and I was trying to get them to draw exactly what I have here on their circle, how would I describe it? Well, I'd say, okay, put a dot on your circle and then draw an arrow starting at that dot that goes, what? A bit sort of down, sort of to the right. I mean, it's going down and to the right now, but if I picked my dot to be somewhere else, like over here, my arrow wouldn't be going down and right. Or if I pick my dot over here, the velocity at that point would be straight up. So all these directions, what do they all have in common? They're not all down and to the right, but they are all what we say is tangent to the circle. And remember I said before that if we kind of zoom in here, the line sort of follows the circle for a little bit. You might want to use the word parallel. It sort of seems like right here, just near the dot, the velocity is parallel to the circle. Now, it's not quite correct to use the word parallel because that word is supposed to be only used for straight lines, and this circle is definitely not a straight line. But we have another word we can use in its place, and that word is tangent. Tangent is sort of like parallel, but for curvy things. So what does the object's instantaneous velocity look like? It is tangent, which we can sort of think of as meaning parallel, to the circle. And another way to think about this without having to use that fancy word is we can think about the center of the circle. Well, the center of this circle is let me do this in a different color. Center of the circle is about here. And if I draw a line from the center of the circle to where my object is, that line is the radius of the circle. And you'll notice that between the radius of the circle and my velocity is a right angle. So another way to describe the velocity is we can say it's tangent to the circle, or we can say it's perpendicular to the radius. Okay, so let's ask a few more things about this object. Is its speed changing? Well, we said at the beginning we were going to imagine something moving in a circle at constant speed. So by definition, its speed is not changing. And you can certainly twirl an object in a circle in that manner so that it always has the same speed. There's no reason why the object might need to be going faster at one location and slower than another location. So is its speed changing? No. Is its velocity changing? Well, the answer to this one is yes. And remember, speed and velocity are similar, but they are different. Speed is a scalar, whereas velocity is a vector. So if we say this object was traveling at 3 meters per second, then that means up here it's going 3 meters per second, and down here it's going 3 meters per second, and over here it's going 3 meters per second, and around this side it's going 3 meters per second. So you can see the speed is always the same. But if I instead asked about its velocity, being a vector, velocity has magnitude and direction. So over here, it's going 3 meters per second left, and over here, it's going 3 meters per second down, and over here, it's going 3 meters per second to the right, and over here, it's going 3 meters per second up. So you can see that the velocity is always changing because its direction is changing. And the final thing we might ask is it accelerating? And the tempting thing to say right off the bat is no. We often lean towards thinking of acceleration as speeding up or slowing down. And since this thing has constant speed, we want to say no, it's not speeding up, it's not slowing down, it's not accelerating. But that would be incorrect. Acceleration is not simply a change in speed. Acceleration is a change in velocity. So because its velocity is changing, it is accelerating. In fact, you might remember that the definition of acceleration, or of average acceleration, is change in velocity over change in time. So as long as the velocity of something is changing, it has acceleration. And this mass on the end of a string is no exception. Now the next thing I'm going to ask about is what would the free body diagram look like from a side view? So we've been looking at this from a top view, but let's go and look at a side view. So here is my mass, and it's going to have the force of gravity acting down on it. And over here somewhere is my athlete who's actually grabbing onto the cable and pulling it. I'm not going to draw the athlete because a true free body diagram only has one object in it. But there will be sort of a force coming over here towards the athlete. And if we pretend the athlete's not swinging this thing too fast, then there'll be a bit of a droop, you might say, to the string. So the string won't be totally horizontal. It'll be kind of going up at an angle like this. So there's my tension force in the cable, the string. Now, if this was it for the free body diagram, this thing would experience a net force. And you can see here the net force would be to the left. We can illustrate this maybe a bit better by splitting Ft into components. So Ft has an x component and a y component. And so this y component of Ft cancels out with Fg. And so our net force, the leftover force, the thing we're left with, is this guy here, that x component of Fg. And indeed, these are all the forces acting on this object. So there is a net force. And in this case, it's towards the left, which is where we said the athlete was, sort of at the center of the circle. One thing we often do in these problems is we put a little star or an asterisk to show where the center of the circle is. And so the thing I want you to realize here is that there is a net force, and that's this red guy that we drew here. This x component of the tension is the net force. And it is pointing towards the center. Now we happen to draw the mass being on the right-hand side of the athlete, but if we had decided to draw the mass over here on the left-hand side of the athlete, then we would find this net force going to the right instead of to the left, but it would still be going towards the center of the circle. Okay. Now let's do a little bit of math here. Let's try and find a formula for some of these things. We've talked about the speed, we've talked about the velocity, we've talked about the acceleration. Let's see if there's a way to actually find some of these things. So we'll start with speed. Well, we know the speed of an object is the distance it travels divided by how long that takes. Well, in the case of an object moving in the circle, it can travel any distance we want depending on how long we let this person swing it for. But let's just look at a certain length of time. Let's look at one rotation. So if it goes once around a circle, we'll imagine we're watching it or we're observing it for one full rotation, then the distance is going to be the perimeter of the circle, also called the circumference, which can be calculated with the formula 2 times pi times r, or pi times the diameter, because diameter is 2r. So 2 pi r is the distance it would travel if we let it go around the circle once. So the next thing we want to know is, well, what's the time it would take if it goes around the circle once? Obviously, this is going to be different for different objects in different scenarios, but there's a special symbol we use for the time to go once around the circle. You'll use this term in mathematics as well. Whenever there's something, an object or a function that repeats the same thing over and over again, kind of like our mass that's going around in a circle again and again and again, or like a sine wave that repeats the same pattern again and again and again. We have a term that we use for how long it takes to sort of do one cycle before it starts to repeat itself. And the term we use is the period. So you can talk about the period of a sine wave, or you can also talk about the period of an object being swung in a circle. And the period is the time it takes to go around once, or the time it takes to do one cycle before it begins to repeat itself. And period uses the symbol of capital T. Okay, so we figured out a formula for its speed, but what about its acceleration? Okay, that's kind of the next thing we might want to find. Remember I said there's sort of three things going on here. We looked at its speed, we looked at its velocity, and its acceleration. Velocity is a little bit hard to find a formula for because, as we saw, velocity was always changing. As this thing goes around the circle, the velocity always changes its direction. So it's sort of hard to find a formula for the velocity, at least for the direction part. But let's see if we can find a formula for acceleration. Well, for starters, let's remind ourselves how acceleration is defined. Right? Velocity was the distance over change in time. Acceleration is the change in velocity over the change in time. So maybe we can use this formula we know about acceleration to try and find a formula for it. But first of all, let's focus on how the velocity of the object changes as it goes around the circle. We talked about this before, but we haven't really drawn it yet. So let's look at the velocity at different points. Well, let's say if we take the object up at the top of the circle here, and we want to draw its velocity. Okay, so we said, again, remember, what the velocity has to do is to get this to the next point on the circle. The next point is right over here, so we've got to head in that direction when we're drawing our velocity. Okay, and a little while later, the object will be over here in this part of the circle. And at this point, the velocity is going to be going straight down. And a little while later, the object will be down here, at the bottom of the circle. I'm just drawing it at a few different points in the circle. And here, the velocity will be going straight to the right. And a little while later, the velocity will be over here on the right side of the circle. And the velocity will be going straight up. So that's the velocity and kind of showing how it would change over time. Notice again, we said this before, the direction of the velocity at any time is tangent or parallel to the circle. Or perpendicular to the radius. So the reason we were looking at how the velocity changed over time was because change in velocity tells us a lot about acceleration. So let's look at the acceleration of this object too. Now, this is not exactly a proof of the direction of acceleration, but it's a bit of an argument I'll make here. If we look at the object, say, at this point in time, its velocity is going down. And where the velocity needs to go to a little while later is to the right. So what's the change in its velocity going to look like? Well, it needs to go more to the right. So the change needs to be kind of to the right. So because this change is going to be to the right, it actually turns out that the acceleration at this moment in time is to the right. So if I drew the acceleration here, I'd have an arrow going to the right. And if we look down here, the velocity is going to the right. But a little while later, it's going to need to be going up. So what is the velocity's change going to have to look like? Well, it's going to have to be an upward change. It's going to need to go more up than it was before. So that hopefully helps to convince you that the acceleration at this point is up. And similarly, the acceleration over here is going to be to the left, and the acceleration up here is going to be down. So I'll label these. The blue ones are the velocities, and the red ones are accelerations. Now look which way all of these accelerations point. They all point towards the center of the circle. Remember, we often use a star or an asterisk to show the center of the circle. And that's not a one-off, that's not a coincidence, that's a very important fact about circular motion, is that the acceleration points towards the center of the circle. In fact, it's such an important thing that we give this type of acceleration a special name. It's not just called A, it's AC. And the C stands for centripetal, which means towards the center. So it's an acceleration towards the center. centripetal acceleration. Which means, like I said, towards the center. Okay, so we added a few extra things in there that we didn't need to, but they'll be important for later. So let's just recap. Even though it may be traveling at a constant speed, anything traveling in a circular path is still accelerating because the direction of its velocity is always changing. Even if the magnitude of the velocity, the speed, isn't changing, the direction is. So our end goal here is to come up with a formula that allows us to calculate the acceleration of an object in uniform circular motion. Remember, we already came up with a formula that let us calculate the speed. That's this guy here. And then we decided that the acceleration is always change in velocity over change in time. So we started talking about, okay, what does the change in velocity look like? And that's when we kind of came up with this diagram here, seeing how the change in velocity was sort of always towards the center of the circle. And so now I want to take these ideas, put them together, and see if we can come up with a formula that actually will crunch some numbers for us and tell us how to find the magnitude of these velocities as this object goes around the circle. So what we're looking at here is, again, another top view of the circle, just like we had over here. But I'm just looking at a section of the circle, just the section of the circle from, say, over here to there. So it's sort of like we took a photo of the object at one point and then the photo of the object a little while later. And we're comparing those two moments in time. In this case, let's say that the object is moving clockwise instead of counterclockwise like we used to have. Okay, so what I'm going to do is draw the velocity of the object at this point, and then the velocity of the object at this point a little while later. And I'm going to call those the initial velocity and the final velocity. Okay, now the next thing I'm going to do, if we're trying to find acceleration, remember that the acceleration depends on the change in velocity. So I'll actually just copy that formula out again, so I have it to reference over here. And then we'll think about how we might get that change in velocity. Well, remember that the change in anything is final minus initial. So change in velocity is velocity final minus velocity initial. Okay, well, if this is VF and this is VI, then to do VF minus VI, that's like doing VF plus the opposite of VI. Remember, to subtract a vector, we add the opposite. So I'm going to take my VF here, and to it, so head to tail, I'm going to add the opposite of VI. So same length as VI, but heading in the opposite direction. Okay, so there is VF and the opposite of VI, head to tail, so they're being added. VF plus minus VI, or VF minus VI, delta V. So the resultant of all that is going to be delta V. And the resultant, remember, goes from start to finish. So there's where I started. And here's where I finished. So that guy is delta V. So next up, I want to kind of you guys to notice that we have sort of two triangles here. There's this blue triangle with my velocities, and there's this black triangle, which is basically the path that, that the object was following when it was moving in a circle. Now, the black triangle is not technically a triangle. It does have sort of one curved edge. But what I want to do is, for now, I want to make that curved edge go away, and I want to pretend that this black one is an actual triangle. This might seem a bit sketchy, pretending this is a triangle when it clearly isn't, but I'll describe later on in the lesson why I think that's an okay approximation to make. Remember, a lot of physics is not about being able to solve absolutely everything, but being able to figure out what things you need to solve and what things you can kind of ignore. So coming up, we're going to be interested in the distance this thing traveled. From here to here, it travels this distance around there. We call that the arc length, and it's often given the symbol S. But because I like this to be an actual triangle and not have that curved side, rather than focusing on this piece, I'd rather focus on this piece here. Now, those are not going to be exactly the same length, but they'll be close. So I'm going to say that this straight line is approximately S. It's not exactly S, but it's approximately S. And we'll talk more about why that's an okay approximation later. Okay, so now I have these two triangles, the black one and the blue one. One that looks at the object's path and one that looks at its velocities. And I want to start dealing with some angles here. So what I'm going to do is say, let's say this angle down here is theta. Right, so this is sort of the angle from where we first looked at the object's velocity to where we next looked at its velocity. That's theta. And I want to see, if I know that this is theta, what can I use, how can I use that to give me information about some of the angles in this triangle? Well, to do that, I'm going to draw a new line that kind of connects these two triangles in a way. I'm going to draw a line that goes this direction here. So this line is going to be perpendicular to the radius. Here, this is the radius of the circle. So I'm going to draw a line that's perpendicular to that. And it's going to connect to that first point in my blue triangle. I'm going to do this line in red. I'm going to extend it quite a bit too. All right. And so we made sure that we drew that line perpendicular to the radius of the circle. Okay, so now here I have a right angled triangle. So that means all three sides need to add to 180. But since this side is 90, that means these two sides need to add to 90 as well. So if this side is theta, this side will be 90 minus theta. Okay. Now I want to look at this angle over here. see if we can figure out what that angle is. Well, from here to there is 180, because that's a straight line. And right here is a 90-degree angle. Remember, when an object's in circular motion, the velocity is always perpendicular to the radius of the circle. So if this whole thing is 180, and that's 90 minus theta, and that's 90, then this bit over here that's left over should be 180 minus 90, because of that right angle I have there, and minus 90 minus theta. So 180 minus 90 minus 90 minus theta turns out to be good old theta. So this angle here is the exact same as this angle here. And it sort of looked that way from the diagram, but now we've been able to prove it. So let's see what else we can do with this. Let's look at this line here and this line here. Well, that red line is perpendicular to the radius of our original circle. This blue line was VI, which is this guy up here, and that's also going to be perpendicular to the radius of the original circle. So, if these two lines are both perpendicular to the same line, that means they actually have to be parallel with each other. So, because I have this line and this line are parallel, I see there's a bit of a Z pattern forming here with two parallel lines and a line that crosses them. So I can use my Z rule from geometry, which says the two angles in the Z have to be the same. So if that top angle is theta, then this angle in here needs to be theta as well. And I didn't note it before, but this is, that's VI there. It's backwards, but it has the same magnitude as VI. Okay, so now I want to look at these two triangles a little more closely. This one over here, which I'm calling the pizza triangle, and this one over here, which is the triangle with all my velocities, they have some similarities. They both start with theta as one of their angles. And then my pizza triangle has two sides on either side of theta that are the same length. Both of those are the radius of the circle. And on my blue triangle here, I have two sides on either side of theta that are both the same length. VF and VI are going to be the same. At least their magnitudes will be, because we're in uniform circular motion, so speed is constant. So that means that these two angles have to be the same, since these two sides are the same. And these two angles will have to be the same, since these two sides are the same. And then since this theta is the same as this theta, that actually tells me that the blue triangle and the black triangle, the pizza triangle, have the exact same angles. They both have theta here. And then they'll have the same angles here, 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 and here. All four of those will be the exact same number. So there's a special word for two triangles that have all the same angles. They're not identical triangles. because as you can see, my black triangle is a lot bigger than my blue triangle. So they're not congruent, as we might say in math. But they are what we call similar. These two triangles are similar triangles, which means they have the exact same angles. Now, one of the important things we know about similar triangles is that the ratios of their sides are the same. So what that means a couple different things. It means if, for example, this side, opposite theta, was half the length of this side beside theta, then that same would have to be true for the black triangle. This side would have to be half the length of this side. And it also works if we go sort of across from triangle to triangle. So if this side, opposite theta, is twice the length of this side, opposite theta, then that has to be true for every other set of sides in the triangles. So this side would have to be twice this side, and this side would have to be twice this side. So in similar angles, you could say the ratios of sides are preserved. So what that means is, for a moment here, it's a little confusing because these two sides are given different lengths, or at least we've got different symbols for them, VF and VI. We know that VF and VI happen to be the exact same number, so I might just rewrite these as V. The speed the object has here is the same as the speed the object has there, because we're talking about uniform circular motion. So I can say that the ratio, because again we have similar triangles, the ratio of this to this is the same as the ratio of this to this. And remember, this side is just r, the radius of the circle. So writing that ratio down, I can say delta V over V equals S over R. This over this equals this over this. Again, we're using this sort of odd fact or a suggestion that this side and this curve are the same length, which does seem a bit weird at this point, but I'll argue why I think that's okay later on. Okay, so now we're into algebra. If I rearrange this and isolate delta V, I get delta V equals SV over R. Well, why am I isolating delta V? Remember, the whole point here is to find acceleration. And acceleration is the change in velocity over change in time. So finding an expression for change in velocity, delta V, is going to be helpful. So now that I've got that expression for delta V, let's go back in and plug through that formula. So acceleration is change in velocity over change in time. Delta V is SV over R over change in time. or SV over R delta t. Now, let's look at this. S is the distance the object traveled from initial to final. S was the distance it traveled. So what I have in here, S over delta t, is the distance it traveled divided by how long it took to do that. So that is v. The distance divided by the time is the speed. So that means I could replace S over delta t with v, which gives me v over r, or v squared over r. So what I've shown is that the acceleration of an object as it moves at constant speed from here to here along a circle is v squared over r. Now I've omitted the vector hats in this last line because although they were kind of useful early on, the directions were really important when we were kind of drawing out these original triangles. This formula does not actually tell us the direction that A will have. This formula can only take us so far. It only tells us the magnitude. And remember, we said before that the acceleration for an object in uniform circular motion was always towards the center of the circle. And we've kind of shown that again over here. We focus on an object sort of on this top part of the circle over there, right? We just drew the top part of the circle to start this derivation. And when we found delta V, we found that it was going straight down. So if I'm near the top of the circle, delta V is straight down. Well, acceleration, the direction of acceleration is the direction of the change in velocity. So if delta V is going straight down when I'm at the top of the circle, then acceleration has to be going straight down too. In other words, towards the center of the circle. So we mentioned this term before, but this is called a centripetal acceleration, or AC. Now the last thing that maybe remains to be addressed here is this whole thing about S up here. So while it seems a little sketchy to say that these two lengths are the same, it seems less sketchy if theta gets really, really small. So imagine I had a circle. We'll draw a semicircle like this. If I'm looking at a point here and a point here, and instead of going all the way around this arc, I just draw a straight line from one to the other, you'd say, well, that is ridiculous. That is a totally different distance from here to here than going around that corner. Total shortcut. Fair enough. But if I take 2 points that are a little bit higher, from here to here, still different distances, but getting similar. If I take 2 points right near the top, say there and there, and I draw a straight line between them, that's almost exactly the same length as going around the curve. So as these points get closer and closer together, this straight line gets closer and closer in distance to actually following the true arc. So what that means is as theta gets smaller and smaller, bringing these 2 points closer and closer together, it gets more and more reasonable to say that this and this are the same length. Now I've drawn this diagram here with theta being pretty big, just so we had lots of space and could see the angles and stuff. But notice that my final result doesn't have theta in it anywhere. So I could have picked this to be any number I wanted, and it wouldn't have changed my end result. So while in this diagram it doesn't look very fair to say that this and this are the same, let's say, well, I could have picked theta to be 1/1,000,000th of a degree. In that case, these are going to be indistinguishable from each other. And changing theta, again, doesn't affect my form or my calculations in any way. Theta doesn't even appear in here, let alone the final answer. So because my final result doesn't depend on theta, I could pick theta to be anything I wanted. And if I pick it to be something really small, it's fair to say that S and delta S are essentially the same. Okay, so the idea here is that we have kind of shown that when an object is in uniform circular motion, all we had to use was the definition of acceleration and a little bit of geometry skills. We've shown that its acceleration is its speed squared divided by the radius of the circle that is its path. So, the acceleration of an object in uniform circular motion is the formula we have just derived, v squared over r. But there's another way we can write this formula. Because remember earlier on in this lesson, we found that the speed for an object in circular motion was 2 pi r over t. So, in place of speed in this formula, I can write 2 pi r over t. And this becomes, if I square everything, I get 4 pi squared r squared over t squared. And then I'm dividing that all by r. Rather than getting two fractions involved, I'll just condense it all into one fraction. So there's a little bit more going on in this formula, but notice that I have an r squared up top and a regular r on the bottom. So I can cancel out one of those r squareds on the top. And therefore can rewrite this as 4 pi squared r over t squared. So there are two ways I can write the formula for centripetal acceleration. V squared over r, or 4 pi squared r over t squared. Note that the change in velocity in our diagram was, right? We were up here at the top of the circle. The change in velocity was down, which means towards the center. The change in velocity was towards the center. Therefore, acceleration had to be towards the center as well. Reason for that is because acceleration is just the change in velocity divided by a scalar. So delta v and acceleration have the same direction. So when delta v is towards the center, acceleration is towards the center as well. Now, if acceleration is towards the center, it turns out that means the net force would be towards the center. Because net force is mass times acceleration. There's only two vectors in this formula, net force and acceleration. So because they're more or less equal, except for that factor of a scalar, they have to have the same direction. So there's a lot of things that are towards the center. The change in velocity is towards the center. The acceleration is towards the center. The net force is towards the center. So that's why we've come up with this special word, which I alluded to before, that means towards the center. And that word is centripetal. A centripetal acceleration is an acceleration towards the center. A centripetal force is a force towards the center. And this is the same word that we were using up here for these accelerations. We called them AC for centripetal acceleration, meaning towards the center.